All right, in this video we're going to talk about the third of Newton's laws, and this is my favorite. It's actually really interesting to talk about. It's written this way. It says if two objects interact, the magnitude of the force exerted on object 1 by object 2 is equal to the magnitude of the force simultaneously exerted on object 2 by object 1, and these two forces are opposite in direction. So let's take a look at this example, someone hitting a wall with their fist. Now, we know how painful this is, right? We can imagine how painful it is. Hopefully you haven't actually done this, but we can draw two pairs of forces on this. They are called the action, reaction forces. Okay, so first, let's draw the force of the fist on the wall. So that force is on the wall. So I'm going to put my free body diagram on the wall, and the force of the fist on the wall is in this direction. So we can call this force of fist on the wall. Well, Newton's third law says for every action, which is the fist pushing on the wall, there has to be an equal and opposite reaction. So ask yourself, where will the force on the fist be? Will it be on the fist itself, or will it still be on the wall? Well, your answer should be it would be on the fist. And if you question that, go ahead and look around your room and find, and you maybe close the door and punch the wall. And if you don't believe that the wall exerts a force on your fist, after you've punched it, I think you will believe it, because your fist is going to hurt. And it's only going to hurt because the wall has pushed back on your fist. And so we can draw a second force. I'll do this one in blue on the fist. And that's an equal length vector, and this is the force of the wall on the fist. Okay, these are referred to as action-reaction pairs. You can see that they're equal in length, and they're opposite in direction. Okay, and the third thing is they act on different objects. This force acts on the wall, that's the force of the fist on the wall, and the force of the wall acts on the fist. So I did not draw them on the same object. Let's take a look at a cool demo that demonstrates Newton's third law a little bit differently. One thing that's interesting about the hand hitting the wall example is that what if the wall could not push back with as much force as the hand pushed on it? So the hand pushes on the wall, but what if the wall can't push back on the hand with enough force to equal the force of the hand? Then the wall crumbles. In other words, if you can hit the wall harder than it can hit you back, and then the wall will break. So that's an implication or an application, I guess, of Newton's third law.
So rockets, we've all seen rockets with the space shuttle take off, but how exactly does that work? Well, we're going to explain how it works very quickly by introducing a guy named Sir Isaac Newton. He lived about 300 years ago, British physicist, great haircut, and he came up with 3 laws of motion. And we're going to talk about his third law of motion, and to show you how this is going to work, we're going to be launching a Shaw rocket, which is kind of handy. This is our special limited edition Express Shaw rocket, and what we're going to do is we're going to launch it using a special rocket fuel that I've mixed here at the H.R. McMillan Space Center. Not something we recommend you folks try yourselves at home or the office. We're going to mix this together and try and explain what Newton was talking about. His third law of motion talks that for every action there's an equal and opposite reaction. So what we're trying to do is to create an action inside our rocket. Our equal and opposite reaction is hopefully our rocket taking off across the stage with a very large explosion, which is what we want. So what I've done is I've filled this rocket full of some fuel. I've poured most of it out, and what I've left inside are just some vapors. We're going to attach this to a specially designed safety cord, and we're going to ignite our rocket much in the same way that they ignite a real rocket. And we're hoping that we're going to get an action. In this case, the action is going to go this way. Our equal and opposite reaction is going to go in the opposite direction. So we're going to get this nice and tight, get this all ready to go. I'm going to put my safety goggles on, get ready, and we might as well do this. We might as well dim the lights. So we'll dim the lights, and in the darkness here, we'll see if we can get this rocket ready to go. Light our barbecue lighter. We're going to go from 5, 4, 3, 2, and 1. Well, a fairly successful rocket launch. It's going to blow some smoke rings for a little while, but you would too if that just happened to you. To learn more about rockets and Newton's other two laws of motion, come down and visit us at the H.R. McMillan Space Center. For The Express, I'm Cam Cronin.
So when we're looking at this video, it's actually really interesting what's happening. This is Newton's third law in action. So what's happening is the gas inside the bottle is coming out this way, right? So our two forces here is one, it's the force of the bottle on the gas, right? So the bottle is pushing the gas out, and that force is acting on the gas, and that's in that direction. So this is the force of the bottle on the gas. But Newton's third law says there has to be an equal and opposite force, the reaction force. So the reaction force is just going to be the opposite of this. It's going to be the force of the gas on the bottle, and that force is going to act on the bottle, and it's going to act in this direction. So now we have the force of the gas on the bottle. And we can see that this is the only force acting on the bottle. So then this is the net force, and so the bottle accelerates in this direction, the gas accelerates in this direction, and Newton's third law, again, is confirmed in kind of a cool way.
Many microbeads on a metal surface, which provide a very low rolling friction for a metal sled to move on. A rubber band is being used to attach the sled to a launching mechanism.
What you're going to see in this demo is another way to describe Newton's third law. The launching mechanism is this frame here, and it's going to launch out a metal bar that's going to shoot out this way. The metal bar has half the mass as the metal frame. So the metal frame is going to apply a force on the metal bar, right? We could say there's a force of the frame on the bar, and that's going to go in that direction. Well, the equal and opposite force is the frame of the bar, the force of the bar on the frame, and that's going to act on the frame. And that's going to be in the opposite direction. Those forces are equal and opposite. So force of the bar on the frame. But what's interesting here, and one way we can see Newton's third law in a kind of a different way, is that since the frame is twice the mass as the bar here, that the frame will go backwards at half the speed the bar goes forward. And you can think of that as a consequence of Newton's second law, which says that the net force on an object equals its mass times the acceleration. Both objects have the same net force. So F net is the same since it's an equal and opposite force, but since the mass of this one is twice the mass of this bar here, the acceleration of this is going to be half. In other words, if we look at the red one, it's got a mass of 2m, so it will have to have an acceleration of 1/2 a to equal the net force. And the blue one has the same net force. It's got a mass that's just m, so its acceleration will have to be 2a. Sorry, it will just be a for them both to equal the same thing. Okay, so here we see this is going to have half the acceleration backwards as this one. All right, so let's watch.
It adds tension so that when it is cut, it's going to launch the metal sled. This is a demonstration of Newton's third law of motion. For every action, there's an equal and opposite reaction. So the action of the rubber band pushing on the metal sled launches the sled to the right, and the launching mechanism is the equal and opposite reaction is going to go to the left. Now you can see the metal sled launching to the right goes twice as fast as the launching mechanism. That's because it has half as much mass as the launching mechanism.
So I just wanted to take a look at the Newton's third law activity that's on iTunes University. Just go through this quickly. You're going to be, in this activity, you're just going to be identifying the action-reaction forces on several different situations. So here we already saw our example. The fist hits the wall hits the fist. So what would the reaction force be for the head bumps the ball? You should draw the arrow in and say, and realize that the reaction force is the ball pushes back on the head, or that ball bumps head. Okay, so and hence that's why after hitting a soccer ball, a player's head will kind of recoil back on this. So this is how this activity works. So let me know if you have any questions. Newton's third law we'll talk about more in class, and hope this was fun.